Start now.
So
Finally.
is that already now?
Yeah.
Okay. The minute starts from now.
30 minutes, okay. Hi everyone, thanks for coming to my completion seminar. My PhD title is Climatology of Tropical Cyclone Extreme Wave Heights. In tropical regions, tropical cyclones or hurricanes or typhoons are the most intense meteorological phenomena and have important societal impacts. Extreme waves generated by these systems can cause damage to offshore structures and coastal settlements, can cause coastal flooding, beach erosion, and play an important role in the design criteria for engineering projects, risk assessments, and insurance purposes. There is no global analysis of waves generated by tropical cyclones. And our motivation was developed an understanding of the climatology of the extreme waves associated with these systems. The methodology of this study has four major parts. The first one is update the wind vortex model of Holland et al. So, including asymmetry and a variable wind and flow angle to have a more realistic tropical cyclone wind field to be used in the wave generation. Then a broad range of parameter combinations of idealized tropical cyclones were used to force the spectral wave model WaveWatch tree to generate an extensive synthetic wave field database. This database was used to parameterize a fetch equation to calculate the significant wave height spatial distribution in a tropical cyclone and develop the parametric wave height model. The last part is the extreme wave height analysis. We did simulation of wave heights for each track point for all possible tropical cyclone tracks globally. And we estimated extreme wave heights for historical data and future climate projections. We did many thousands of years of simulations, and the best computationally efficient method was using this parametric wave height model that we developed. Let's start with the first part. Most of the parametric wind field models for tropical cyclones use a fixed wind flow angle to provide a more realistic tropical cyclone wind field. The Holland vortex model was improved using a variable wind and flow angle parameterized from results of Tamise et al. And the asymmetry was included, adding half of the velocity of movement. Our parameterized wind and flow angle has this cosine form. We can see that the amplitude is function of the velocity of movement of the storm, and we have an offset function of the radial to maximum winds, the Rmax. In these panels, we have the wind and flow angle contour plot within a storm from different velocity of movements. We have in the top left the stationary storm, and in the bottom right, we have a storm with a velocity of movement of 12.5 meters per second. We can see that when we increase the velocity of movement of the storm, the wind and flow angle decrease ahead of storm. The storm direction is upwards, and the wind and flow angle increase behind the storm center. And these parameterized results agree with the results from Tamise et al. This parametric wind field was validated against H wind using wind parameters from Arbitrax data sets. The Hage winds is a post-storm reanalysis, and the Arbitrax is a best track data for tropical cyclones. The ability of these parametric wind field generate the waves was also validated. We use the parametric wind field to force the WaveWatch 3 model to hindcast historical hurricanes in North Atlantic. We did validation of the wave parameters results, HHS, the peak period, direction, and spectra against the NDVC boys data. Results compare reasonably well with the Boy data for integral wave parameters and directional spectrum. These results provide confidence in the performance of the updated wind parametric model for use in simulations of wave generation. In this figure, just an example of the hindcast of the Hurricane Ivan. On the left, we have a wind parametric wind field with the Boy's location marked by these black triangles. And in the middle, we have the HGS in the vertical axis and the HGS time series with the data measured by the Boy on the right side of the storm, this Boy here, on black, and data simulated by the WaveWatch 3 in red. We can see for this case, we have an underestimation of the peak waves by the model. On the right, we have the energy spectra for the Boy at the top and for the WaveWatch 3 simulation at the bottom. We have a reasonable agreement for frequency and direction. Now that we have a wind vortex model updated, it's ready to use for the generation of synthetic wave field data set. For the tropical cyclone wave field generation, we use a moving grid implementation of the WaveWatch 3 to run a broad range of combinations of idealized tropical cyclones to generate an extensive wave field database. This moving grid approach was a more computational efficient method to have a fine grid of a large spatial extent to get all stop track. Regarding the WaveWatch 3 configuration, we use the ST4 package with a grid resolution of 2 kilometers, 32 frequencies, and 36 directions. To specify the wind parameters range to using the simulations, we use the more frequent values on the Arbitrax database for North Atlantic and Western Pacific basins. For the velocity of movement, you use a range between 0 and 15 meters per second. For the radial to maximum winds, the Rmax, we use 15, 30, and 60 kilometers. For the R34 radius of gale force, we use 200, 300, and 400 kilometers. And you use the central pressure equivalent to maximum winds between 20 and 80 meters per second. The combinations of these parameters generated around 400 tropical cyclone simulations. In the figures, just an example of the joint distribution of these parameters for North Atlantic and Western Pacific. For all simulations results, the HGS and wave group velocity are functions of the Vmax, maximum winds, and velocity of all movement, VFM. In the left panel, we have the HGS on the vertical axis, function of the velocity of all movement on the horizontal axis. We can see that the HGS increase until reach a limit and then it starts to decrease. These limits occurs when the storm is moving too fast, around 12.5 meters per second. We can see the same pattern for different wind velocities. We have the Vmax increasing upwards, with the maximum, with the largest waves related to the maximum Vmax. We can see the maximum Vmax in this light blue color here. On the right, we have the wave group velocity on the vertical axis, also function of the velocity of movement. We can see that when we have the velocity of movement greater than the wave group velocity, the storm is moving faster than the wave group, and the peak waves are left behind the storms. These results agree with the concept of an extended fetch. Waves generated in intense wind regions can remain aligned with the wind for a longer time and propagates ahead of the storm. For storms moving faster than the waves group velocity, the waves are left behind the storms and hedge decrease. Compared to results of Young, 88, that did a similar study using a second generation wave model, the inclusion of the nonlinear terms in the wave model that we use now, we are using a third generation wave model, means a stronger transfer of energy to longer waves. Wave growth can be sustained for faster moving tropical cyclones than previously believed. Young, in his results, got the waves wave growth until 10 meters per second of the velocity of all movement. And in our study, we got results showing that the waves can grow up to 12.5 meters per second of the velocity of all movement. Okay, now that we have the wave field data set, we can use this data set to develop the parametric wave height model. Following the concept of Young, an equivalent fetch for each synthetic tropical cyclone. What is that?
Your watches is drawing on the screen.
Oh, I can't see this. Oh, I cannot see this.
Yeah, don't worry about it.
Yeah, okay, just leave that. Following the concept of the equivalent fetch, for each tropical cyclone wave field, each tropical cyclone wave field was calculated using the Johnson fetch limited growth relationship. We did we modify a little bit this relationship, adding a calibration term, this alpha, that was set equals 1 in the fetch calculation. But after the validation, we set this alpha to 0.89 for using the parametric wave height model. Results confirm that the extended fetch within a tropical cyclone is defined by both the Vmax and VFM, as well as there is a dependence on the spatial scale parameter Rmax. In addition, in our study, we found that there is also a dependence on the spatial scale parameter R34, the radius of Gale's force. In these panels, we have the fetch contour plot in kilometers, function of the velocity of all movement in the vertical axis and Vmax on the horizontal axis. We can see that the largest fetch are related of VFM between 10 and 12.5 meters per second, and Vmax between 30 and 55 meters per second. We have the Rmax increasing from the left to the right, and R34 increasing these panels from the top to the bottom. We can see that when we increase the Rmax and R34, the fetch also increases. Our parameterized fetch equation has this third order polynomial form, function of the maximum wind, Vmax, and velocity of fall movement. The scale correction factors lambda to R max and gamma to R34. Using the modified Jones-Swap relationship, the maximum HGS associated to the fetch is calculated. This maximum HGS is applied to a normalized HGS by maximum HGS spatial distribution for the selected synthetic tropical cyclone wave field to determine the bidimensional HGS distribution within the storm. And then we have our parametric significant wave height model ready. In this picture, we have an example of this normalized HGS by maximum HGS spatial distribution for a tropical cyclone with the parameters Vmax 15 meters per second, VFM 5 meters per second, R34 300 kilometers, and Rmax 30 kilometers. With these parameters, using the fetch equation, we can calculate the fetch and then calculate the maximum HGS, and applying the maximum HGS in this bidimensional distribution, we can find the HGS for this wave field in any place of this diagram. The validation, we validated this parametric model against observational data. We use altimeter and buoy data for historical hurricanes in North Atlantic, typhoons in Western Pacific, and tropical cyclones in Northwest coast of Australia. We can see here in the figure one, the comparison between the HGS calculated by the model, parametric model, and the HGS measured by the buoys. We can see a positive bias for the calculated in the data calculated by the model, and it was expected because the parametric model has limitations. This model assumes fully developed storm in deep water with no changes in storm direction. To address this overestimation, we applied a reduction factor, setting that the calibration term in the Jones-Swap relationship to 0.89. Here, just one example of the comparison against the altimeter data for the same Hurricane Ivan. On the left, we have the wave field calculated by the parametric model, and in magenta, we have here the track of the altimeter. It is on the right, we have the HGS measured by the altimeter in magenta for each track of the altimeter. And we have the HGS calculated by the parametric model for each track point of the altimeter. We can see for this example, underestimation of the waves ahead of the storm in this area here, and our overestimate of the waves behind the storm center, this area here in the low wind side of the storm. Here we did not apply any calibration factor, any reduction, and we can still see overestimation in the peak waves. And for this example, we have here probably a misleading in the position of the track. Now an example of the comparison with the buoy data for the same Hurricane Ivan. On the left, we have the wave field calculated for each track point. And the buoy data used to compare is in the right side of the storm, this black triangle here. On the right, we have the HAS time series with the buoy data measured by the buoy in black and the data simulated by the parametric model in blue. We have in this case an overestimation of the waves around 2 meters when the storm was passing closer to the buoy during this time here. Again, no calibration factor was applied here in this step. These first three parts of this research were published at the Ocean Engineering Journal last year, in 2023. The title is Development and Validation of a Parametric Tropical Cyclone Wave Height Prediction Model. Now that we have a parametric wave height model ready, we can go to the last part, that is the extreme wave height analysis. For the extreme wave height analysis, we use the wind parameters from a synthetic tropical cyclone track database called STORM to force the parametric model to the generation of the HGS for each of the tropical cyclone bases. This STORM database is a statistical tropical cyclone model based on historical tropical cyclones based on IB tracks data. We use 1,000 years of tracks between 5 and 45 degrees of latitude, north and south. The extreme value analysis we did through the direct return estimate applied to 1,000-year annual maximum values, resulting in a 100-year return period significant wave height, the HS100. This predicted HS100 was validated against independent extreme value analysis studies for diverse statistical methods and data sources. We did the same approach using the version of the synthetic tropical cyclone track database for future climate called STORM-C to determine the future global changes. To run the parametric wave height model, we need the tropical cyclone parameters, the track position, longitude and latitude, the Vmax, VFM, Rmax, and R34. Track position, Vmax and Rmax, we got from the STORM database. We use just Vmax greater than 33 meters per second to be above of Saffir-Simpson hurricane wind scale. For the direction of the propagation and velocity of movement, we calculated that using the track positions from the STORM tropical cyclone database. And for the parameter R34 is not provided by this synthetic database. And then we calculated the R34 based in a relationship between the R34 and Rmax from the IB tracks data for each tropical cyclone base. In this table, just the relationships we use for the different tropical cyclone ocean bases. Here an example of the simulation results for the Eastern Pacific Basin. We have the synthetic tropical cyclone tracks from STORM database. We have here for each track point the Vmax, velocity of movement, and Rmax. On the right, we have the maximum HAS calculated by the parametric model for each of these track points for this Eastern Pacific basin. For this basin, the maximum Vmax from the synthetic tropical cyclones database is 76.9 meters per second, and the maximum HAS related to that calculated was 19.3 meters. It's for 1,000 years of data. For the extreme value analysis, the maximum HAS generated by the model for each tropical cyclone track point was stored at the grid locations of 0.1 by 0.1 degree grid. These data were pooled to form a 1 by 1 degree grid, and the annual maximum was determined on this 1 degree resolution grid. The 1,000 years of annual maximum were ordered from the largest to the smallest, with the HAS 100 ranked at the 10th data location. We call this direct return estimate. This predicted HAS 100 was validated against independent extreme value analysis reported in literature, and the confidence level interval was calculated using the bootstrap technique. We did 500 random repetitions. Here are an example of the extreme wave results for the Eastern Pacific. We have on the left the contour plot of the HAS 100, and on the right the confidence interval span for these results. We can see that the regions with the highest HAS 100 has confidence interval plus minus 1 meter. However, the confidence interval can reach plus minus 3 meters in regions where the frequency of tropical cyclone is low, like this northern part of this basin. For this basin, the maximum HAS 100 predicted was 16.8 meters. Here in this slide, we have the global distribution of the extreme wave heights across all tropical cyclone basins. In the Northern Hemisphere, we can see that the Western Pacific and North Atlantic have the largest extreme waves globally, with similar maximum values of HAS 100 of 70.4 for Western Pacific and 70.2 meters for North Atlantic. Eastern Pacific and North India show lower values for this hemisphere, with 16.4 meters for Eastern Pacific and maximum HAS 100 of 15.5 meters for North India. Southern hemisphere shows lower values than the Northern Hemisphere. The maximum values of HAS 100 estimated for South India and South Pacific have similar magnitudes, 14.6 for South India and 14.7 meters for South Pacific. In the table, just the maximum Vmax, maximum HAS for 1,000 years, and the maximum HAS 100 calculated, predicted for all basins. These results were published at Nature Portfolio Journal Scientific Reports this year in February. And the title is Global Tropical Cyclone Extreme Wave Heights Climatology. Now that we present the extreme wave height analysis for the historical data for the present day, we are going to show the extreme wave height analysis for the future projections. The future climate projections, we use the wind parameters from the storm database, the synthetic tropical cyclone track database for future climate. This synthetic track database has 4 global climate models, datasets, with resolution between 25 and 50 kilometers. And we use the CMIP6 high emission scenario SSP 585 between 2015 and 2050. Same method was applied to the tropical cyclone HGS simulations and the HGS 100 estimates. We did for the 4 GCMs separately. The ensemble median of the HGS 100 was used to compare with the historical results. In the pictures, we have the contour plot of the HGS 100 for each global climate model, and at the bottom we have the HGS 100 ensemble median used to compare with historical results. Example for the Eastern Pacific Basin. Here we have the contour plot of the HGS 100, just the ensemble median for all tropical cyclone ocean basins, and in the left, and on the right, the confidence interval span for each basin. We can see that in regions with the highest HGS 100, the confidence interval is good. It's ±1 meter. However, as happened with the historical data, the confidence interval can reach ±3 meters in regions where the frequency of tropical cyclone is low, like in the southern part of the South Indian Basin or here in the northern part of the Eastern Pacific Basin. In the table, just the maximum values of the HGS 100 estimate for each tropical cyclone basin for the future climate, and the same data for using the historical data for the present day. We can see a tendency, a trend in increase the HGS 100 for almost all tropical cyclone basins, with a decrease for North Atlantic and North Indian. I'm going to tell more about this next slide. Here we have the global changes in extreme wave heights under future climate conditions. To calculate these global changes, we just did the difference between the HGS 100 estimated for future climate and for historical data for each grid point. We have the trend of increasing in wave heights in red, and a trend in decreasing of wave heights in blue. We can see a tendency of increasing extreme wave heights in Western Pacific, Eastern Pacific, South Indian, and South Pacific tropical cyclone ocean basins. And we have a tendency in decreasing extreme wave heights in North Atlantic and North Indian, but it's small in some parts of North Atlantic, decreasing just 0.5 meter. But it's significant in Bay of Bengal in North Indian. We can see a decrease up to 2 meters in the wave heights. These results agree with the trend of changing in extreme maximum winds estimated by Blumendahl. And these results were submitted to Nature Climate Change is under review now. Now the conclusions related to the first 2 parts. The more realistic wind vortex model, including asymmetry and a variable wind flow angle, plus the use of a third generation spectral wave model, which includes the nonlinear terms, was essential for the construction of the synthetic wave database and develop the wave height parametric model. About the parametric model, despite some limitations, it was computationally the best efficient solution to simulate wave heights in each tropical cyclone track point for all tropical cyclone ocean basins. We did many thousands of years of simulation. And about the extreme wave height analysis, in conclusion, for regarding the present day tropical cyclone waves climatology, we have the Western Pacific and North Atlantic presenting the largest extreme waves globally, and South Indian and South Pacific ocean basins having very similar climatology. Related to changes under global warming conditions, we can see a tendency in increasing magnitude of the extreme waves for almost all tropical cyclone basins, with exception for North Atlantic and North Indian tropical cyclone ocean basins. Thank you for listening, and I'm open for questions.
Thank you, Guisela. Right on time.
37. It's the same that I did in my rehearsal with Ian.
When you practice, then sure. It shows. Maybe I will start it because I have many, right? And I don't want to just dominate everything. So just a couple to start. You had 4 parts, right?
Yeah.
The part 1, the wind vortex model. What is the novelty of that? That's the model which already existed. It's just you validated it, and that's the novelty.
The wind vortex model, we just update that, improving, adding a variable wind flow angle, and also adding the half of the velocity of fall movement to have a more asymmetric wind vortex.
All right.
Yeah, it's a different alpha.
Yeah, okay. So it's a different coefficient. Questions? Simon?
Yeah, excellent presentation, Guisela, and a lot of compute time. Just about following from Alex's question on the vortex model, yeah, the Holland one with all its updates and so on is very commonly used. So did you look at others? I think there's other asymmetric ones. I'm not sure, but there's Willoughby, and there's some, but other ones are dynamic, like Keppert and Wong. They're dynamic. You're using parametric, and they've got asymmetry, the dynamic ones. But did you look at others, like, I don't know, Willoughby or Knapp?
Yeah, we checked others, but we decided to stay with the Holland that it's widely used. Yeah, and we think it'd be better just to try to upgrade this, adding this variable wind flow angle, and it worked reasonable well. Then after the validation, well, okay, let's keep.
And the thing that I liked about your scaling of the fetch was that you actually scale it against R34, because it's a much better predictor than Rmax. Rmax is not as reliable. So, and a lot of wind, and especially for waves, they don't include R34. So that's good. The other question, just about when you showed the future projections, and extreme wave heights are increasing pretty much everywhere except Bay of Bengal. I mean, even in North Atlantic, there's some. I guess it's so high variability. They're increasing and they're decreasing. Is it because the Bay of Bengal has warmer ocean and it's predicted to get even warmer, or what are the reasons? I mean, it's just standing out.
Yeah,
I know it's a very highly vulnerable to tropical cyclones, but so is Northwest Australia. But maybe because it's warmer, is there any reason for it?
yeah, it's more because the Vmax, because
Okay.
the maximum winds are lower
Right.
in this high emission scenario from the synthetic storm database that we used, and the velocity of movement and the Rmax in R34. In that case, it don't have so much weight.
Mhm.
In this case, we saw that the maximum winds are lower, and because that our waves are low as well. But they put some explanation, Blumenthal.
Yeah, Bloomingdale actually. So in the Bloomingdale database, they actually say that it's probably the area that's most questionable in terms of the future projections, in terms of the variability between the GCMs as to what's going to happen there. And it's and the frequency of storms in that area is lower than the other areas.
Yeah,
as well.
Not much observations also in that area, probably.
Yeah, I also had a question about the Bay of Bengal, because part of that is shallow area, right? And therefore the heat content of the ocean, I don't know, it's smaller. Is it taken into account? They say in Waywatch 3 that it, I don't know how
No,
shallow it is.
it's all deep water.
Yes, so our parametric model is for deep water.
But I think, Alex, I think it does come into. I think that's some of the reasons for the so I guess lack of confidence in the GCMs is related to the water depths in that area as well.
Joey?
Guisela, thank you. I had a question about the same slide. So I don't know too much about climate and tropical cyclones, but how do we interpret those big red parts over there? Does that mean that the intensity of the tropical cyclones are projected to be higher, or does that mean that tropical cyclones basically occur more east, more south, more north? How should I interpret?
You mean the trend?
Yeah, so
It's
for instance,
related to the tropical cyclone. Yeah, the trend is related to the maximum winds and the intensity of the tropical cyclones, but also depend on the frequency of the storms as well. And if you have low frequency of storms, we can have a difference on the trend of the HS as well. I don't know if you want to start talking.
no, sort of.
Or what, asking.
Yes, thank you.
Yeah, I had a same question or maybe same comment, right? So the statistics can change because you have the same number of storms, but the wave height actually changes, right? Or you have fewer storms, right? And that can probably be two different reasons, but obviously in this picture they're not shown, right?
Gisela, just comment on that.
Yeah.
Whether it's an increase in Vmax or an increase in frequency of the storms.
We increase the frequency of the storms and the Vmax as well. We can have increasing in the waves.
But what causes it here? What's happening in the future? So what does Storm C say about? Are there going to be more storms, or are they going to be more intense storms?
No, the case here is not that we have more storms. The case here is that we have more intense storms, like more category 4 and 5. And we can have lower frequency. We can have less storms, but we are having increasing the intensity of storms. We have the predicted more intense storms, more category 4 and category 5, and that's why our it predicted H as 100 would be higher.
So just a comment, I just remember reading a long time ago, probably 5-10 years ago, that when the predictions of tropical cyclones frequency intensities were not as good, and they said that, look, yeah, the intensity is going to increase, but the frequency might decrease. So that's what you are also looking at now. So is your prediction that the frequency of tropical cyclones would actually decrease in the future climate? So is it sort of confirmed, or what?
Yeah,
I guess
we
nothing's confirmed. But...
we are using a synthetic tropical cyclone track that shows that we have in some basins decrease in the frequency, but an increase in the category 4 and 5. And we are just using this synthetic database to calculate and estimate our wave heights. If the synthetic tropical cyclone track that we are using has a different intensity in winds and frequency, our calculation will be different as well.
So I think none of us here are tropical cyclone climatologists, so we can almost say anything. I think the jury's still out.
I think still out. That's
Yeah, I think so.
Okay.
Ellen?
Yeah, just a quick question. You said that you use the years to altimeter as well as the void data to validate your P model. Why did you choose those two, and why only one altimeter is available, but it's publicly? Was there a particular reason? And
I use
more than those two, and I missed it.
I use some altimeter data. More, this case that I showed is for Hurricane Ivan, but I tried to use for some hurricanes, and I use the altimeter data for typhoons as well in the Pacific. It's better to use the altimeter data because you don't have any void data. Close to typhoons, it was difficult to find. In altimeter, we have some with the track crossing the tropical cyclone with wind fields, wave fields.
So this was just an example.
Oh, okay. Right.
Yeah, but
Did
this
you
was an
use more than
example.
just use-
No, yeah, I used at least I think 10 or 12 K using the altimeter data.
Yeah, I'm not sure if online people can hear me. So if you have a question, please raise your hand or just put it into the chat. Any more questions? Guisela, I have a few
I
more.
don't know, I have to check if there's something in the chat.
Guisela, you mentioned in your conclusions as well, inclusion of nonlinear term in your synthetic database obtained by means of WaveWatch 3. What does that mean? WaveWatch 3 always has nonlinear term.
We use the third generation of the, we use the WaveWatch 3, but when we compare with the results from Young that use a second generation
okay,
model,
all right, yep.
that in that case, that second generation didn't have the nonlinear terms, the wave-wave interaction, in the model.
Maybe the last one from me. We will see if there is anything else. From the online, slide 12. Can we go to slide 12?
Go through. So click direct. Okay, 12.
Yes, so this plot, one-to-one plot, right? In principle, the agreement is good between the model and the measurements. There is obvious bias, which is not small, and most of the points are above the line, right? So the model.
Yeah,
estimates-
positive bias.
Question. Do we know which ocean is which, right? Because you compare three different oceans here: North Atlantic, Western Pacific, and Australian coast, right?
Yeah, this case of for the boys in the North Atlantic.
Oh, okay. So we
Yes.
don't know how
No,
Australian
No,
tropical
no,
cyclones sit here.
but these ones for boys in North Atlantic. And yeah, we have this positive bias of that's why we use a reduction factor in our parametric model.
Guisela, explain to Alex, we're not surprised by that. That's what we expected it to do. Why did we expect that to happen?
Yeah, because the parametric model has a lot of limitations, and one of them,
Pretty good.
yeah, it's in deep water with no changes in storm direction.
It's not so much a limitation. I mean, it's the assumption. So it's for a fully developed storm that's moving in a straight line. If the storm deviates in some way at all, then the parametric model just immediately changes direction. So it's always fully developed. Whereas a real storm, which turns or intensifies, so it'll always be lower than small.
Yeah.
That's what we expected it to do. Yeah.
I also noticed that in East Pacific, the future trend is that the wave height goes down, right? And then from what I remember, that East Pacific tropical cyclones are much bigger in size than West Pacific. So the fetches are bigger. So what does that mean? The size is going down, or the winds will not be as strong?
No, but Eastern Pacific will have a trend in increase of the waves.
Slightly.
I think in the previous slide there was a decrease. Can you go to the previous slide? Yeah. Oh, okay.
Yeah, just for North Atlantic and North India, we have
All right.
decrease in the maximum HS 100.
Okay, the online audience. It's very
Alex,
Any more questions? Any questions?
this is Enrique, Alex.
Yeah.
Can you hear me?
Yep.
Awesome. So Gisela, well done. Great presentation. I have a question that has to do with that slide. It also has to do with the uncertainty. So I didn't really see a measure. I mean, you have the confidence interval there. So those differences that you see there, what level of confidence do you have exactly in the future climate that, which of those changes there you think they're more conclusive and which are inconclusive? And then the follow-up question is, can you establish objectively confidence intervals for the results of your model?
Yes, for the changes in the future, we have more confidence indicates in areas where we don't have like a big increase and decrease, like area in light red and light blue. If you look in the results for the HS 100 for the future climate, in the areas where we have the highest highest HS 100, our confidence interval is higher, it's better, and with just plus minus 1 meter. And these areas are the same that we have low increase or low decrease. And in the same areas, we have a confidence interval better than the areas where we have like low frequency of storms and the confidence interval is so high. like plus minus 3 meters.
Gisela, just say something.
Red.
You haven't shown it because of time,
Oh.
but you have actually calculated which of these points are statistically significant.
No, yes, but I don't have.
Yeah.
So,
Okay, and then again, the follow-up question is objectively, can you calculate confidence intervals that can be applied to the output of your modeling system, of your parametric model, essentially?
that's. Yes, and we did that in the paper, in the publication. We have this.
Okay, so I'm looking forward to the paper. Thank you, Guisela.
Thank you.
Okay, I don't see any more questions from online audience. That's your last chance. No? Any more questions here? No? I
Yeah,
guess
I don't
that's
think
that's
so.
the end. Thank you, Zola, and we will,
Thanks for all from, yeah.
we will need everybody online to leave except Enrique and Alberto.
Yeah, guys, thanks for coming. You just need to leave. It's Zoom.
And Alessandro.
Thank you all.
Of course, right.
Now, Alessandro, Alberto, and Enrique needs to leave. Yeah, I need to go. Obrigada a todo mundo aí do Brasil, ok? Eu tenho que sair agora e todo mundo pode deixar.
Parabéns, Grisa, estamos saindo.
It's blood chocolate too, did you get him? This blood chocolate too, did you?
Ah, yes, did you like it?
Very good.
Good idea?
Maybe a couple of minutes.
Okay, no worries.